Okay, welcome everyone. So we're doing ocean acidification today. Ocean acidification is what people refer to as the other CO2 problem. So first of all, a reminder, what is pH? Because it's all going to be about acidity today. So pH is, you take the concentration of H plus ion in water, in seawater in this case. You take minus the log 10 of that, and that is the pH. And pH lower than 7 is acidic. Does that ring a bell from kindergarten and all that? It does, great, okay. One of these things that there isn't much uncertainty about, so you could see this part is the decrease in pH that we already observed from 1950 to 2000, so there's not much question about that. The width here is the uncertainty, so there's not much uncertainty. And these are the projections. So of course, depends on whether we're talking 8.5 with a large CO2 emission or something else with less of a CO emission. But these clouds, again, reflect the uncertainty within that scenario between different models. And you can see that there isn't very much uncertainty in the ocean becoming more acidic as the CO2 increases. So it's one of these things in which there's not much uncertainty in the acidification of the ocean. There will be some uncertainty in terms of the effects on biology and other things. And of course, there's a big uncertainty on what emission scenario will end up being relevant, but beyond that. These are again observations. So what do we see? You see the trend in each of these different locations pointed out by these arrows, and you can see that it's becoming acidic everywhere, basically. It's pretty straightforward. Great. So here are a few words on the biological consequences of ocean acidification. So these are the types of creatures that are being affected. We're thinking about plankton, corals. They all have calcium carbonate skeletons that may be affected. Here's an example. So this is a coccolith. So it's a small plankton, and this is the results of an experiment of growing these in lab conditions under higher and higher CO2. So you remember the 280 was the pre-industrial concentration, and then they grow it all the way to 750. And what you see here is that these plates that make up the skeleton of this become larger and larger and probably distorted too. So you might think that larger is better in this case, but any change to this is not a good thing, because they've been evolved for millions of years and found an optimal configuration, and you don't want to change things for them at this point, now that they've adapted. And clearly this makes a huge difference. Look at the difference between the 280 and the 750. 750 is not necessarily out of the question, I think, by the end of this century. And at the same time, their volume, so this is only the skeleton, but the volume includes sort of the meat of these creatures, and you can see that the volume also increases. So this makes a big difference for this particular species of plankton. And this is another example. So this is a pteropod. People refer to that as a sea butterfly. It's a very small pea-sized snail, and you can see it right here. And this is under a microscope. The edges of the snails are being affected by dissolution. I think you see it better in the next one. This is an experiment in which the snail was put into this acidic water that represent the end of the 21st century, and they significantly dissolved within 45 days. You can see the evolution from day 0 to day 45. So a very significant effect on these creatures, which are a meaningful part of the food chain for salmon, krill, whales, and so on. Okay, so now we can go and plot the pH changes and think about them a bit. Okay, let's move on to the next phase. So you see this change. Can someone tell me by what percentage did the concentration of H plus change so far? Yes? 25%. 25%. Now, don't you think that's amazing? It changed by 25%. That's a lot, right? The pH only changed by a fraction, but it's a log scale, so the actual change is very big, not negligible, interestingly enough. Okay, and that's what projected in the future. So you could see 2100 minus 1986 and so on. So a change over about 100 years. And it's very dramatic given that this is a log scale. Now that we know that such a small change corresponds to 25%, you can understand that this is a huge increase in the H plus concentration. And this shows that the change isn't just at the surface, it actually penetrates into the deep ocean. So these are two scenarios. This is a very optimistic one. This is more realistic perhaps. And you can see, as function of the depth into the ocean, you can see that the changes penetrate all the way to 1 kilometer. So it's not just the surface ocean. So anything deeper than that would also be affected. So very significant changes. And now we want to understand how this affects calcium carbonate dissolution, because biology depends on calcium carbonate, right? The skeletons are made of calcium carbonate. So let's try to understand that. That first part is pretty straightforward. So let's see how that goes. So calcium carbonate dissolution. So here's the reaction we're thinking about. We have CaCO3 in equilibrium with calcium 2 plus and CO3 2 minus. So this is the carbonate ion, this is the carbonate ion, the calcium ion, and this is the solid calcium carbonate. This could be these skeletons or the sediments at the ocean bottom that are made of calcium carbonate, and there's an equilibrium between them. And when there is such a chemical equilibrium between the two, we can express it in the following way. So there's the dissolution constant, Ksp, that is a function of temperature, pressure, other things, and it should be equal to the product of calcium 2 plus times CO3 2 minus. So when we put things in brackets, you remember this is now the concentration, say in moles per liter, and this product should be equal to this constant in equilibrium. And if this product is less than the constant, what would happen? Go ahead, say it.
The reaction would proceed towards less than, so it goes to the right.
Right, if this product is not large enough to be equal to this, we would need more of these ions, so the reaction would go in that direction, right? Okay, so based on that, we can define the constant omega, the saturation state, omega, which is defined to be the calcium 2 plus times the CO3 2 minus divided by Ksp, and omega less than 1 implies dissolution. Okay, now what we need to do is understand, so our goal, understand how increased atmospheric CO2, so CO2 gas, changes the concentration of basically CO3 2 minus, and therefore affects dissolution. So we will understand how the changes in CO2 affect the pH and how the pH affects the concentration of CO3 2 minus, and that's how we'll understand how dissolution would depend on atmospheric CO2. Let's see, so let's formulate our goals. So we want, first of all, to understand what's known as the calcium carbonate CO2 dissolution. We just did. Then we want to understand the ocean carbonate system. How is the pH affected by atmospheric CO2? How this carbonate ion affected by CO2? Then we'll talk about the buffer effect. This is the effect that allows the ocean to absorb a very large amount of CO2. And then we'll talk about the positive feedback. Turns out that the warmer ocean releases CO2 in response to the warming. And so that's a positive feedback on the warming because it would lead to more warming. And finally, we'll talk about the long-term fate of anthropogenic CO2, how the ocean carbonate system eventually can absorb all the CO2 and get rid of it over a time scale of thousands of years. That's the plan for today. Any questions? Okay. Yes.
If the K value is related to the equilibrium concentrations, is there a way that we specify that? Because just looking at the equation, then it seems like omega would always be 1 if we don't specify it.
Here, let's put it back on the screen so we can talk about it. In equilibrium, it's always 1. In the ocean, it turns out it's not necessarily in equilibrium even today. But I think the idea is that we're changing the CO2 concentration. That will affect the concentration of this, and that will affect the value of omega. This would lead to dissolution that would then restore the value to 1. Okay, so more of this penetration. So this is now observed changes, and you can see by the shading that the pH is decreasing and the value of omega is decreasing. So what happens here is the contours are the value of omega in 2002, and the shadings are the change, and the changes basically indicate that omega is becoming less than 1, so we're going out of equilibrium and toward more dissolution of calcium carbonate, presumably making it more difficult for some of these plankton to grow their shells, or we'll talk about the biologic effects and how complicated they are a bit later.
Ocean acidification is a process that has also been called the evil twin of global warming. It's a problem that...
Great. Okay. Do we love chemistry here? Do we have many chemistry? Here we go. 1. That's a lot for a class. Hopefully there's one more maybe. Well, let's start. So remember, our goal is to understand how CO2 changes in the atmosphere affect dissolution and pH in the ocean. So let's see how that goes. So for that, we need to discuss the ocean carbonate system. So we start with atmospheric CO2, gas. And this is an equilibrium with dissolved CO2, which we denote by this. And then the dissolved CO2 interacts with water. So that would be the next step. And then we can write that reaction as CO2 dissolved plus H2O is in equilibrium with H2CO3, which is the carbonic acid. So this one is the carbonic acid, okay? It turns out that it's difficult to tell the difference between this one and this one. So it makes, when you try to measure things, so we define a new variable that is the combination of both, and that would be our H2CO3 star, that is defined to be the sum of the two. So CO2 dissolved plus H2CO3. So Henry's law written in terms of the new variable would be written the following way. CO2 in gas form is in equilibrium with H2CO3 star, which we've now defined. So this is Henry's law. This is the gas exchange law. Okay. Once we have H2CO3 in the water, it starts releasing H pluses. It's an acid, right? And an acid releases H pluses. So the first release would be H2CO3 is in equilibrium with H plus HCO3 minus. This is referred to as the bicarbonate ion. And then the next release would be HCO3 minus is in equilibrium with H plus and CO3 2 minus, the carbonate ion. All right. And then in addition to all of that, we have the dissociation of water itself. So H2O is in equilibrium with H plus OH minus. So let's just count how many equations we have. We have 1, 2, 3, and 4. So 4 equations. And how many unknowns? So let's see, we have CO2 gas appears in our equation. We have this H2CO3 stars. There's HCO3 minus, CO3 2 minus, H plus, and OH minus. So 1, 2, 3, 4, 5, 6, 6 unknowns.
In equation 3, after that H plus, is it like multiplying those, or is it?
No, this should be a plus. Thank you. Okay, so 6 unknowns and 4 equations is obviously not good news. We need 2 more equations. Can someone suggest something? Yes?
Don't we know the CO2 gas? No?
That's a good question. So let me explain what we're thinking. We're thinking there's a volume of water that is in equilibrium with the atmosphere, and we're trying to calculate all the concentrations in the interaction between the two. They should be in equilibrium. So in equilibrium, we should be able to determine all quantities involved. So for that, we'll need to specify some things and calculate others. In some situations, we might want to specify the CO2 gas. In other situations, we might want to specify something else. We'll see in a second. Yeah. Okay. So one constraint that's clearly still missing is the conservation of mass, right? The number of carbon atoms should be conserved in these reactions. We're not losing any and we're not gaining any. And the other thing that should be conserved is charge. So charge, electric charge conservation and carbon mass concentration are both conserved. This would give us the 2 missing equations, and then we'll be able to solve this carbonate system. What do you think, Lux?
It's right.
That did not say exactly the same thing. I'm glad to hear. I'm copying from that person anyway. Good for you. Okay, good. Okay, so let's see. Let's start with mass conservation. And it's really carbon mass conservation. Okay. So we can define something referred to as the total CO2. Denote that as, say, CT. And that's equal to the concentration of H2CO3 star plus the concentration of CO3 2 minus plus HCO3 minus. So each of these is in mole per liter, say, and this way we have a count of all of the carbon atoms in the system. So now we've counted all the carbon ions, and this should be conserved under these reactions. If you release a proton from these acids, it can change the number of carbon molecules. And it turns out that this one is smaller. So we would later make the assumption that this is small and get rid of it, but for now we keep it in. Okay, that was the easy one. Now we're getting to charge conservation. Okay. So let's see. Charge conservation, first of all, says that the ocean is basically electrically neutral. There are positive ions, negative ions. The net charge should be 0, obviously. So we can write that. Let's write the statement that the net charge of the ocean, say of a liter of seawater, is 0. So that would tell us that 0 is equal to say all the pluses, H plus, plus, Na plus, plus K plus, plus 2, magnesium 2 plus. So you see that this one is counted as 2 because it has 2 positive ions. So if we're counting ions, we take the concentration of this ion, multiplying it by 2 to get the number of charges as opposed to the number of ions, okay? Looks like you understand that. So plus 2 calcium, 2 plus, and then we have minus. So minus HCO 3 minus. Let's put brackets here. Plus 2 CO3 2 minus. Same idea as before with the factor 2. Plus OH minus. Plus chlorine minus if you want. Plus other negative ones, period. So you take all the positive ions and all the negative ions, sum them together, and this should give you a 0 because the ocean is neutrally charged in principle. That's the beginning. Okay, let's see. Now comes the interesting part. So some of these ions, so our purpose is to see how in these reactions, when the pH changes, how these reactions change, okay? So the pH will change because the CO2 changed, and this will change some of these reactions. Some of these ions are not going to depend on the pH. For example, if you have NaCl, you put it into seawater, it just dissolves completely. Regardless of the pH, it will never combine. While if you look at HCO3, the release of this second H plus does depend on the pH concentration, right? So these are referred to as strong acids and bases and weak ones. The weak ones are those whose release of H plus, for example, or concentrations in general depend on the pH. So let's just delete all of those that are strong and don't depend on the pH. So this one doesn't make a difference for us, and this one is not important, and this one is not important, and this one doesn't matter, and this one doesn't matter. And I think that's it. So we're left with 1, 2, 3, 4 elements. And this would be, the ones that are remaining would be referred to as the carbonate alkalinity. So that's a value that looks like, a quantity that looks like this. Here, alkalinity C is HCO3 minus plus 2 CO3 2 minus plus OH minus minus H plus. So we're taking the negative ones minus the positive ones, keeping only those that are affected by the pH and have to do with the carbonate system. We've actually neglected a few more that are also weak, but they're less important. These are the main ones. So once someone gives us this value, it should basically be conserved under the carbonate system reactions. Just like the number of atoms should be conserved, this quantity should be conserved because it represents the conservation of charge. So now we have our equations number 5 and 6. So this would be number 5, and this would be number 6. And now we have 6 equations and 6 unknowns, and we should be able to solve the system. Okay. The one thing I want to do is write it as a set of equations. So let's do that. So the carbonate system equations. So what we did there is write it as reactions, but if we want to solve things, we need to write it as equations. So that, for example, would look like this. We have KH is equal to H2CO3 star divided by CO2 gas concentration. This represents Henry's law. So given that if the ocean is in equilibrium with the atmosphere and the gas exchange has brought it to equilibrium and it doesn't change anymore, then the ratio should be equal to this constant, and this constant should depend on, temperature and so on. But this is a known constant, so now we have an equation relating this concentration to that concentration, similar to the dissolution constant that we had before. Okay, the next one is K1, which is equal to H plus times HCO3 minus divided by H2CO3 star. So you can see this is the release, this is the reaction representing the release of the first H plus. And when that one is in equilibrium, this ratio should be equal to this constant. And then we have the second release, so K2 is equal to H plus times CO3 2 minus divided by HCO3 minus. So that's the third equation. The dissolution of the dissociation of water gives us Kw equal to H plus times OH minus. And then we have two more equations for the mass conservation and charge conservation. So alkalinity C is equal to HCO3 minus plus 2 CO3 2 minus plus OH minus minus H plus, and the total CO2, the mass conservation for carbon atoms, is equal to HCO3 minus plus CO3 2 minus. You notice that this one doesn't come with a factor of 2 because now we're counting the number of carbon atoms instead of the charges. Plus H2CO3 star. And this is the complete set of the carbonate system equations that we will solve today. Why are we doing this again? Just to remind you. Because we want to see how changes in CO2 would affect the pH, which is the concentration of our H plus. So H plus is one of our unknowns. We want to know how the acidity will change. We want to understand the effects of CO2 on calcium carbonate dissolution. For that, we need this carbonate ion, so we'll solve for that in terms of the CO2. So the good news is that we're done with the most difficult part today. And let me just review that using the slide. So CO2 is in equilibrium with the atmosphere, so this is Henry's law. And once you react with water, you develop the carbonic acid, H2CO3. We said it's difficult to tell the difference between these two things, so we defined H2CO3 star as our variable that represents the carbonic acid. Okay. And now the Henry's law is this interaction between the CO2 in the atmosphere and the H2CO3 star. It releases two protons. The carbonic acid releases two protons. These are the two reactions. Water dissociation is another one. So these are the four reactions of the carbonate system written in terms of equations. So this has 6 unknowns and 4 equations. So now we need 2 more. So we said charge conservation gives us this alkalinity that we talked about. And then we have mass conservation. So this thing also needs to be prescribed. And that plus the 4 equations gives us 6 unknowns and 6 equations which can be solved. Okay. Let's see, I want us to look at this and think about the results you plotted, and you'll understand that there's actually a big surprise here, okay? Look at this. As the CO2 increases, the pH, the blue one, decreases. That's not a surprise. We don't understand why yet. We will understand soon. The other one is also surprising. You see, as the CO2 increases, CO3 2 minus decreases. Now, think about it. We have more CO2 in the atmosphere. It's dissolving in the ocean. You would have expected all carbonate species, all ions to increase as a result of that. What happens instead is the CO3 2 minus decreases instead of increasing. Remember why this is critical. This is the one that controls the dissolution of calcium carbonate. This is the one we care about, and it's behaving exactly the opposite from what you would expect naively. We now need to take these equations and solve them in an approximate way. So what we're going to do is take this system, simplify it, and solve it analytically. Instead of what you have is a numerical solution, instead we're going to solve it. It's just like 3 or 4 steps. It's very, very simple. So let's see how that goes. So if you look now at your solution, can you tell me, in the expression that appears for alkalinity, which one is going to be the large and which one is going to be the small contribution? Let's start with the total carbon. Which one is going to be the smallest of these 3? Yes?
H2CO3 star.
The star is going to be small. Let's see, which curve is it here? Green. We're talking about the ocean pH is roughly 8.1. So at this point, the green is definitely below everything else, right? So this means that we might be able to neglect this one. What about H plus? Is H plus large or small? That you can tell from the value of the pH itself. So what does the value of the pH tell you about the concentration of H plus? It's 10 to the minus what? 10 to the minus pH. These things are measured in millimole per liter. Milli is 10 to the minus 3. And the pH is going to be 10 to the minus a lot. It seems to suggest that this one is small. This one turns out also be too small. So we're left with this system where the alkalinity is approximately equal to this, and the total carbon is approximately equal to this. That's all we need to do to be able to solve this very easily. So we made sensible assumptions, and now we're going to use these assumptions to solve things. So solving approximately. So look at this. We have 2 equations in 2 unknowns. The unknowns are HCO3 minus and CO3 2 minus. They appear both there and here, the only difference being that factor 2. So we have 2 equations in 2 unknowns. If we think of CT and alkalinity as given, then we have 2 equations in 2 unknowns, these being the 2 unknowns, and we can easily solve them, right? We could say take the difference between these equations and so on and so forth. And it turns out that what we get is this, HCO3 minus is equal to 2 times the total CO2 minus the alkalinity, the carbonate alkalinity, and CO3 2 minus is equal to carbonate alkalinity minus CT. Okay, next let's look at this equation. This is the second dissociation of the H2CO3. So what do we know and what don't we know? Well, we know HCO3 minus. We know this friend. We know this. We can calculate this directly from this equation. So that gives us a very straightforward solution that H plus is equal to K2 times 2CT minus alkalinity C divided by alkalinity C minus CT. Great. Okay. We go to the K1 equation. So now we know this. And we know this, we can calculate that. So that gives us immediately that H2CO3 star is equal to K2 divided by K1 times 2CT minus alkalinity squared divided by alkalinity C minus Ct. Okay, now we can go to the Henry's law. So Henry's law, we know Kh, it's a known function, and we know the H2CO3 star, so we can calculate the atmospheric CO2 now. So let's write the solution for that. And that's the end of it. So K1 times Kh times 2Ct minus alkalinity, carbonate, squared. Great. We solved for everything. Okay, congratulations. Wasn't hard. You're going to solve something similar in the notebooks. But now we can use this to understand everything. We can use this to understand why CO3 2 minus is decreasing, why the pH is changing, and so on and so forth. Any questions about the analytic solution of the approximate carbonate system? Yes?
I was just wondering, at the beginning of the derivation, we're using the unknowns from before, right, that you wrote down? So all of these were unknowns on the left-hand side?
That's right. So, no, tell me again. I'm not sure I understood the question. Maybe I missed it. Tell me again.
I was asking if, at the beginning of this derivation,
Yes.
for this approximation,
Yes.
all of these left-hand side
These
concentrations,
things.
or
These are
or
the
in
left-hand sides?
the final approximations.
These are the unknowns, yes. Yes, we had, remember we had 6 unknowns in this. Okay, that raises an important question. When we make these approximations, OH minus drops out of the equation, so we don't need to worry about it anymore. So now we have only 5 unknowns, and you can see that in our equations, OH doesn't show up because we dropped it here. This is the only place where it dropped out, so we don't need to worry about this, and we don't need to worry about that. Okay. Now that we've done that, we have only 5 unknowns because OH minus is not an unknown anymore, and we had the right number of equations, and we solved for all of these unknowns, 1, 2, 3, 4, 5. Okay, great, thank you, good question. Okay, so let's just review what we just did. We said, based on the exact solution that we plotted, that there are these things that are smaller, H plus, OH minus, and the H2CO3 star are all small, so we can neglect them. We end up with this approximate expression for the alkalinity, the carbonate alkalinity, and an approximate expression for the total CO2, basically the mass conservation and the charge conservation take simplified forms. And given that, we have now these 5 equations, and we solve for these 5 unknowns. You get the idea. Okay? So let's see what we can do with it now. Okay. So what we want to do now is understand why CO3 2 minus is decreasing. I'm going to go back and just motivate you again, just so that we won't forget. You remember this, okay? So what's happening here? This is the interaction between solid calcium carbonate dissolving into calcium 2 plus and CO3 2 minus, okay? That was the dissolution reaction. And in equilibrium, we have the product of the 2 ions has to be equal to this constant. And we define this omega to be the ratio between the 2, and we said that if CO3 2 minus decreases, so if it's decreasing, omega will become smaller, and if omega is smaller than 1, then we have CO2 dissolution because we need to supply more of these ions, so we need to dissolve more calcium carbonate. So then that's felt by the biology, presumably, or we might be dissolving calcium carbonate at the bottom of the ocean. Both things happen. Okay? So that's why we care about CO3 2 minus. And then I also want to remind you that we were surprised to see CO3 2 minus decreasing with increasing CO2. Why are we surprised there? Because as we add CO2 to the atmosphere, we have more carbon dissolved in the ocean. We expect everything with carbon to increase, but instead this trend is decreasing. So let's try to understand why, how could it be decreasing? It's actually pretty straightforward in terms of what we did now. Any questions about the motivation? So let's see. Let's go over this slowly. We said when the atmospheric CO2 is increasing, we have more dissolved CO2 in the water. This is Henry's law. It's pretty straightforward. Okay. If we have more of this, this reaction would go to the right. When it goes to the right, we get more H plus and more HCO3 minus. Does that make sense? It's simply you increase the left-hand side, the right-hand side will increase too. Okay? So both H plus and HCO3 minus increase. They increase by the same number of ions, the same mole per liter. Okay? But there's a big difference between H plus and HCO3 minus, which is going to make a big difference. So let me explain what that is. The thing is that you remember the H plus, the concentration of H plus is very, very small relative to this one. So when they both increase by the same number of moles, or millimoles, or whichever, the fractional growth in this one is much larger than the fractional growth in this one. So if you ask by how many moles this increased and this increased, they increased by the same mole. If you ask by what percentage did they increase, the percentage increase in H plus is going to be larger because the concentration was lower. That's a critical point. So tell me if there are any questions. Okay. Is that clear? There's a difference in the fraction of growth as opposed to the numerical value of the increment in the number of ions. Okay, so now that we understand that, if you think about this reaction, this is the second dissociation of this thing that produces the CO3. So think about this ratio. So H plus divided by HCO3 minus. These are exactly the same, the things that were involved here. These two things both increased. So you would think that the ratio, because both increased, the ratio would remain the same because both increased. But the fact that one of them is much larger than the other means that the ratio is actually increasing. So to be in equilibrium, this would have to decrease. And this being CO3 2 minus. I'll let you write this down and then I'll say it again. This is a tricky part. Okay. So let's try again. So we had more dissolved CO2, so both H plus and HCO3 minus increased because of this dissociation reaction. It moves to the right. So this and this both increase. Now the fractional growth is different because this was a very small number to begin with. This was a much larger number. So as a result of that, as a fraction, this increased much more than that. So the ratio H plus divided by HCO3 minus did grow, did increase. And now when we look at the next dissociation, or not at the, we just look at, yeah, we look at this dissociation, then this ratio is increasing. To keep us in a steady state, CO3 2 minus must be decreasing. And that's what we saw in the exact solution. That is more complicated to obtain. And because this is decreasing, there would be more tendency to dissolve calcium carbonate now because of the increase in CO2. Right, so the fact that this must decrease means that this reaction actually must go in that direction. As a result of that, when we dissolve CO2 into the ocean, it doesn't stay as H2CO3. It's converted into the other ions. But Henry's law sees this. So as far as Henry's law is concerned, it only sees a small amount of carbon in the ocean, so the ocean can absorb more. So this allows the ocean to absorb a large quantity of carbon, which is why global warming is not as rapid as it might have been if all the CO2 stayed in the atmosphere. So the ocean absorbs CO2. It's converted into H2CO3 until the atmospheric one and this are in equilibrium. But because much of this is converted to other carbonate species, this equilibrium hides a large amount of carbon that is in the form of these other ions. And this effect is referred to as the buffer effect and allows the ocean to absorb much more carbon than it would have been able to do if not for these carbonate system reactions. Okay. According to the exact solution that we saw before in our approximate solution, if you look at the number of ions and molecules here in this case, here, relative to one another, in equilibrium, in pH values that are relevant to the present-day ocean, this accounts for 1% of the carbon, this accounts for 10%, and this accounts for 90%, okay? So now what happens is this. When the atmospheric CO2 increases, this will increase by a certain amount as well. Because this is only 1%, it means that this ion HCCO3 minus, the bicarbonate ion, increases much more than is reflected by the increase of this that is directly affected by the atmosphere. So what happens is the atmospheric CO2 increases, it's converted into this H2CO3 star, but then that immediately is converted to the other species of carbon, and that's why the ocean can hide so much CO2. These are some consequences of acidification. So this is a coral that was grown in acidic water, and you can see that the calcium carbonate melted and these creatures remained naked. And of course, in a normal ecological system, they would be eaten by something very rapidly. They can't survive that. Okay, we talked about the biology being complicated. So without going over this in too much details, and you have the source of the paper right here, the idea is this. This summarizes many other studies, and it says basically, is the response of this species decreasing, increasing, doesn't affect anything, or is it non-linear? It's first increasing, then decreasing, or vice versa. And basically, you see the number of studies that show each behavior, and the bottom line is simply that it's complicated. Some species increase in abundance, some decrease, some behave in complicated way. If you ask what is the effect of acidification on the biology, the answer is it's complicated. So if you think about solutions like geoengineering that say, well, let's put aerosols in the stratosphere to compensate for the warming effect, but that does not reduce the CO2, then ocean acidification in such scenario would be a serious problem because the CO2 might increase dramatically. We've dealt with the warming, presumably, with these aerosols, but we haven't dealt with the other CO2 problem, ocean acidification. Let's talk about response to warming now. Bottom line of the response to warming before we get into details is this. As you warm the ocean, it emits CO2 and provides a positive feedback on anthropogenic greenhouse warming, right? We increase the CO2, that warms the ocean releases more CO2. That's a positive feedback. Why does that happen? Well, first of all, these reaction constants are a function of temperature. So you can see over the range of temperatures from 10 to 20, some of them change significantly, some increase, some decrease. You can see which ones. These are all normalized by their value at 10 degrees so that you can see them all together on the same graph. You can see that even if you keep the alkalinity, so now we know if we keep the alkalinity and the total carbon fixed, that allows us to calculate everything in the carbonate system. But you can see that as you change the temperature, the pH actually drops because these constants that we have in our solution depend on temperature. So what happens is in spite of the fact that the alkalinity did not change and the total carbon did not change, the pH drops down. And if we take the ocean and warm it, it will increase the atmospheric CO2. So look at this. If you just warm the ocean by 10 degrees, the atmospheric CO2 increases by 100 ppm. That's a big effect. As part of ice ages, the ocean warmed and cooled, and that affected the CO2 in the atmosphere. That was one of the effects. There are other mechanisms. But you could see that the warming affects the pH and affects the atmospheric CO2, and there's a positive feedback and so on. I didn't explain why, right? I won't explain, but I'll show you one equation that explains this without getting into the details because I sense that we're beginning to be tired. But I wanted to make sure that the facts are clear, that the reaction constants, the quotients we said it's called, the quotients, excellent, depend on the temperature. As a result of that, the pH will decrease. The ocean becomes more acidic as you warm it, and and the atmospheric CO2 in equilibrium with the ocean will increase, right? So there's a certain amount of carbon in the system. I warm the ocean, more of it would leave the ocean and go into the atmosphere. Let's summarize. Ocean acidification is referred to as the other CO2 problem. It's already robustly observed. I mean, you can see the ocean having become acidic already. We don't have to wait for it. You calculated it. There's 25% more H pluses in the ocean. That's a big effect already observed. There's a potential effect on ocean life. It's basically an unavoidable effect of high CO2 concentration. Unlike other things, there's really not much uncertainty here. The CO2 increases. We could easily calculate the effect on the pH in the ocean. There's the buffer effect, which allows the ocean to absorb more CO2. So on the one hand, that's good news because it reduces the warming. On the other hand, it's bad news because it increases the acidity. There's the positive feedback that the warming provides on CO2. And eventually, CO2 will decrease because as the ocean becomes acidic, it will dissolve calcium carbonate of ocean sediments, and that would restore the pH and the CO2 of the atmosphere back to its original values. That might take thousands of years. So it may not be a solution on a short time scale. Any final question about ocean acidification? All right, let's just call it a day, and we'll see you next time.